This week, we're going to be focusing on the question of what it means or what it can mean for strategy profiles in normal form games to be optimal. In the last video of last week, we saw Pareto optimality, which is one such notion of what it means to be optimal. And if it wasn't clear, in game theory, there is no unique notion of what it means to be optimal, like there is if you have a single objective function. And a notion of what it means for a strategy profile to be optimal is called a solution concept. So Pareto optimality is an example of a solution concept. So solution concept is a kind of class of strategy profiles for a normal form game that we consider solutions of the game. So the most important solution concept for normal form games is called Nash equilibrium. So this is a kind of individualized optimality condition where every player is kind of their individual decision problem is solved. So let's start looking at the definition of this. So we're going to fix a normal form game. So we have a bunch of players. Each player has a bunch of pure strategies, and we're going to fix a strategy profile, which is sigma, and we're going to say that a strategy for some player is going to be called a best response to the strategy profile if that player plays, so TI is a best response to sigma. So TI here is a strategy for player I, sigma is a strategy profile. If the strategy profile formed by player I playing TI and everybody else playing sigma, so here player I is kind of unilaterally doing something different, results in a better payoff for player I, this is player I's payoff function, is better than any other choice that player I could have done. So the notation here is that, so sigma is a tuple of strategies, and by this notation, I mean replacing the ith element of the tuple with some other strategy. And if you read other sources, most sources write this with this notation, which I find kind of disgusting, but it's quite standard. You write sigma minus I to be projecting out the ith element of this tuple and then adding back in this one. So there's an important caveat here that this really means best response. So given that everybody else is playing sigma, tau I is the best thing that player I can do. It does not mean merely that it's a better response. So it's not enough that player I's utility is higher than if they'd played sigma. It has to also be higher than anything else that they could have done. So it was a best response, not a better response. Okay. And a Nash equilibrium is defined to be a strategy profile that for every player is a best response to itself. So what this means is that so here we've taken sigma and then we've kind of updated where the ith player plays sigma I, but that's doing nothing. So that is to say, this is what happens if player I follows the strategy. Their payoff is at least as high as anything else that they could have done, given that all of the other players are still playing sigma. So this is called a unilateral deviation. So every other player except for I is sticking with sigma. And then we say, what happens if we allow player I's strategy to vary unilaterally? And then, so a Nash equilibrium is that for any given player, for every player, if you unilaterally vary just that player's strategy, then the thing that they're already doing is optimal. So the key idea here is that every player is reasoning as though every other player's strategy has been fixed and is known. So it's a bit of a kind of subtle idea of in what sense is this a good notion of optimality. I should say also all of this applies both to pure strategies and also mixed strategies. So all of these definitions work for mixed strategies, but you have to stick an expectation on the front. So we also have pure strategy Nash equilibria and mixed strategy Nash equilibria. Okay, there's a subtlety here because for mixed strategies, it looks like each player's optimization problem is an infinite optimization problem. It looks like that they need to check whether what they're doing is better than every possible mixed strategy for that player, which is a distribution on their set of pure strategies. And there's infinitely many of these. But it turns out quite conveniently, if you fix all but one player strategy profile and just vary one, the resulting function from, so this thing, the thing that for any given mixed strategy here gives you the ith player's payoff, this thing is linear, by basically because the expectation operator is linear. So because this is a linear program, it has to attain its maximum at a vertex of this thing, and vertices of this thing are the pure strategies. So it's actually, in order to be a mixed best response, it is enough that the payoff is higher than every pure strategy. So here tau I is a mixed strategy, but tau prime I is varying only over the pure strategies, and this is enough by linearity for this to be also a maximum for all mixed strategies. There's a kind of related argument to this that says that every pure Nash equilibrium is also a mixed Nash equilibrium. So if you're optimal for unilateral deviations to pure strategies, you must also be optimal for unilateral deviations to mixed strategies. Okay, there is a major reason why Nash equilibria are very important in game theory, which is Nash's theorem. So Nash's theorem is something like the fundamental theorem of game theory, or one of the kind of very, very old and very kind of fundamental facts that motivated the development of game theory. So Nash's theorem says that if you have a finite normal form game, so say you have finitely many players and every player has finitely many pure strategies, then this game must have at least one mixed strategy Nash equilibrium. In general, it can have more than one, but it must have at least one. And this is not an easy theorem to prove. This uses a famous theorem called the Brouwer fixed point theorem, which says that if you have a ball in n dimensions, in any number of dimensions, and then you have a continuous mapping from the ball to itself, then this continuous function has to have a fixed point, so some point that's mapped to itself. I would recommend, if you've not heard of this result before, try to visualize this in 2 or 3 dimensions. Like think about kind of deforming some 2-dimensional or 3-dimensional shape in a continuous way, and try to come up with an example of one that doesn't fix a point, and you'll find that you can't do it. Famously, this theorem is what's called non-constructive, which means that although we have a proof that every game has at least one mixed strategy Nash equilibrium, the proof doesn't give us any hint of how to compute it. And it turns out that actually computing Nash equilibria is extremely difficult. We're not going to talk about this in this course. There's a field called algorithmic game theory, which is quite active at the moment, which is, in general, it's the study of how to compute things in game theory, but computing Nash equilibria in particular is one of the kind of cornerstones of algorithmic game theory. This is algorithmically difficult. Okay. And there's some, so in the next video, we're going to see a bunch of examples of this. So for all of the example games that we have so far, you can actually work out the Nash equilibria. In individual cases, you can actually work them out. It's just that there's no general algorithm to do so, or no general efficient algorithm to do so. So we're going to see a lot of examples of this in the next video. And there's quite a lot of subtlety to do with the interpretation of what it means to be a Nash equilibrium. So like when you say that a certain strategy profile is a Nash equilibrium, what does this really mean? Like in what sense is this a solution of the game? So it's been known since a very long time, since like 70 years ago or something like this, that if you put human players in a behavioral microeconomics lab and get them to play games from game theory, they often don't play Nash equilibria. So this is kind of not predictive for what humans will do typically. One way that Nash equilibrium is often justified is by what's called common knowledge of rationality, which is that all players are rational. So this is like all players are perfect, never make mistakes, they act perfectly according to self-interest and so forth. But also all players know that all players are rational, and all players know that all players know that all players are rational, and so on to every possible degree. And if you break this at some point and you start having doubts at any finite level, then suddenly Nash equilibrium doesn't make sense. This is a kind of old idea. A more interesting idea for me is the idea that, well, if computing Nash equilibrium is so difficult algorithmically, how can we expect our players to play them? Like if we can't write a computer program that will find Nash equilibrium, how can we expect our human players or our algorithmic players to play it? So it's not a good prediction just because you can't find them. Another problem is that in general, a game can have multiple Nash equilibria. We'll see examples of this, and there is no general method to say that one is better than another. And more generally, there is no generally accepted theory of learning Nash equilibria. That is to say, there is no kind of iterative process in general that will converge to Nash equilibrium. So no way in which a bunch of players can interact over time in order to converge towards playing a Nash equilibrium. This can happen in individual cases, just not in general. One setting where Nash equilibrium does tend to work quite well is when you have large populations of players. So there's a field called evolutionary game theory, which is exploring this. So Nash equilibrium is actually quite useful in applications in ecology, for example. Okay, and then that's a lot of generalities, and then in the next video we're going to see some down-to-earth calculations of these things.